so we're very happy today to welcome Professor Ron Fearon from UC Berkeley. Ron has been at UC Berkeley for maybe 23 years now and doing very cool robotics work the entire time, which we'll hear about today. Bachelor and Master's from MIT, PhD from Stanford, and then he saw the light and became a bear. Got an equivalent of an NSF Career Award shortly after he started at Berkeley, and has, like I said, been doing fantastic robots since then. So, welcome, Ron.
Well, thank you very much, Sarah, for the kind introduction. Thank you for inviting me. Thank you for coming to the seminar. I'd like to tell you about the sort of broad overview of the work we've been doing at Berkeley the last 3 to 5 years. What we call Biomimetic Millirobots. These are robots that are palm size or smaller, so milli maybe up to deci or centi or something like that. We started out in micro robots and they got a little bit bigger recently. So let me tell you about some of the things we've done and why we're doing them. Just for sort of a contrast, the conventional robotics approach, which sort of started probably in the 50s, very much you've got an environment here, you sense everything possible you can about the environment. From that, you build up a model of what's going on, and then you act on that, act on what you think is going on, and you end up with robots that look like this. And you can still buy these robots. There've been so that's 50 years now, and they really haven't changed very much. And they got a little bit smarter, but they basically do the same thing. They wander around and look at things and try to figure out what's. They're very concerned about what's in the environment. And the thing we're trying to look at is, well, a lot of things in nature, they may not really care what's in the environment. Think about insects, cockroaches or flies. They didn't evolve to be familiar with buildings, and yet somehow our buildings seem to be full of flies and cockroaches. And why is that? So it's like, did they suddenly evolve a new representation of the environment, and they now know about cubes and doors and things like that? Probably not. They have much lower, much less. I won't say it's much less sophisticated. But a much different approach to the world where they can react to things in ways without having to recognize what's in the environment. And that, in some sense, it's a limitation, but in other sense, it's more robust. You don't care what the environment is, and you can just get your mission done without any care about the environment. That's actually, I think, a powerful approach. And of course, it means just some inspiring robot things, just to give you a flavor. Is there any way to make it any dimmer in the front here? I don't know if you can see that at all. Basically, this robot here going over a very rough surface, it's got no representation of that environment at all. It's just taking advantage of the dynamics and the compliance of the robot to go over there. The other example is from my colleague Bob Full. We see a gecko go up this surface. So the gecko has no idea what's going on that surface. There's actually a smooth patch there. And that smooth patch, it turns out, has got a coefficient of friction. The gecko doesn't adhere to that well at all, and it slips. So it's got no representation of the environment, but you notice it slipped there, but it's got enough upward momentum to carry it through there. So it's taking advantage of the dynamics to overcome. Think about what would the conventional approach be? You climb up there, climb, sense whether you can adhere, take the next step, sense, oh, I can't go anywhere, and then, okay, well, then you're done. So it's an example that in some cases, the less you know, the better off you are. A lot of people really hate that idea, though. If you knew too much here, you'd go. Okay, so this is somewhat of what we think, just in a very vague way. This is certainly still the environment we're interacting with it in a variety of ways, with legs, wings, fingers, and toes. We know how fast we're moving. We know what the force is. So there's some stiffness and impedance relationship with the environment. These systems may be driven sort of in an open loop feed-forward fashion, with various transmission mechanisms, various power oscillators, power driving this whole system. And then the sensors still come in here, but they may come in different ways rather than explicitly planning the motion of a foot, instead tuning the dynamics or the mechanical properties of the system to give you a good mechanical interaction with the environment. So it's a little bit, or maybe a significantly different approach. So I'm going to tell you about just some of the robots we've been making last few years, crawlers and some flyers, and tell you also about how we make them. But maybe before that, just a little bit about why would you want to have really small robots? It seems like they're going to be dumb and can't do anything. It's the usual usual thought about it. Well, maybe they are dumber in some way. Each individual robot can't carry as much computation, but if you can give me 10 kilos of robots and I can distribute that computational intelligence among all those, over 100 robots or over 1,000 robots instead of over one big robot, I claim I can make the same computation available. Some things help as well here, for example, communication, you get your networking effects, cell phone technology. Mobility actually gets better because of your surface volume effects, right? So really small robots, much easier for a 1 gram robot to climb the wall in the ceiling than it is for a 1 kilogram robot. So overall, we think that things get pretty interesting and even better in the small scale. And the application we think about, collapsed building, much better to send in a bunch of small robots to explore that space than try to send in a dog, send in a person, or even a big robot. It's just there's not enough space in there. Someone might be trapped in that car, but you're not going to be able to get to them with a big robot. Okay, so let me start talking first with a couple of flight examples, and then switch over to some of the ground platforms. So, what we've been doing here, we start with a commercially available ornithopter platform. Started out as the iBird, but now it's an AirHawk, so about $30. And we've take basically the transmission out of it and the wings and add on our own tail mechanism, own tail control system, and motor control sensor platform. Sensor platform, we're using it for this board here. We had to build something pretty lightweight with payload capacity of this robot's probably about 1 to 2 grams at the most. So you need very, very lightweight electronics. We've got a big processor, accelerometer, gyro, and radio, and as well a cell phone camera interface, so you can fly around with a camera and do a little bit of processing. The overall device weighs a little over 12 grams. And just make a note here that the big limitation in this is the battery technology. It's for all of the small robots. Pretty much, if you get us a smaller battery that has the same power density, we can probably build some sort of robot that would be able to take advantage of that. Certainly for crawling robots, for flying robots, probably as well. Okay. So what we're going to see is we want to do some very simple system identification. What we found first is we run the robot in a wind tunnel, and we measure the forces as a function of the airspeed and as a function of how fast the wings are beating. We found that our careful wind tunnel measurements tell us that they can't fly. There's a bit of a problem, and the reason we think on that is because the way we mounted the robot, we've constrained it. So when it's flying, it's got a little bit of ability to oscillate freely. When you clamp it in the force torque sensor, it's losing some of those motions that we have in free flight, and therefore the lift force dropped about 20% or so. So the way we get around, we still want to do the system identification. So what we did is we closed the loop around the ornithopter and hover using external vision sensing. And I believe this is the only example I'm showing today where we're using external sensing. All the other robots are running with onboard sensing and control. You'll see a lot of robots you watch on YouTube now where they've got a motion capture system, so they've got complete state information, they know exactly where the robot is, which is fine, except if you need to rescue some people from a buried building, you have to go in there and dig out all the rubble, put up your motion capture system first, which kind of slows things down. So we're interested in general being able to use onboard sensing. So this example, this is just using basically a simple camera system and actually a laptop. It's just aiming at this robot. The robot's got orange painted on it. I'm just going to just show you the height regulation. We use this then as to build up the model, which we use. I'll show you the next part for flight control system. So this is it's actually only controlling one thing, which is the flapping frequency of the wings. So it's just a complete. It's basically an uncontrolled mode with yaw, because there's no actuation on that at all. And it's just doing this stable orbit. The line is the regulated height. And you can see it makes a slow transition up there. So we can build out then a map between the speed of the wings and the we want to do something a bit more interesting with a free flight towards a target. And the way this is set up, so we take the same basic ornithopter platform, and now we're going to add on there's a remote IR sensor that's running at gives about 200 hertz frame rate, and gives a location of four blobs. It turned out that there's some problems with that. We've moved away now to more of a cell phone camera, just because the Weeboat seems to capture some bright lights, and you don't have any way of filtering those out. But it's a nice lightweight sensor on the order of a gram or so. So what we do, there's an IR source here that we're heading towards, and you've got target tracking. That's just looking for the blob, and we predict where the location is. Now, there's several interesting things that are going on this platform. One is that the field of view of the sensor is actually pretty small. So as the robot is going around, it's oscillating because of the flapping, and so it's fairly common that it will actually lose track and won't be able to see the sensor. And when that happens, we use a dead reckoning approach using the onboard gyro rate sensor. So the gyro rate sensor has a drift maybe of even if it's a degree per second, the flight times we're looking at here maybe 10 seconds. You're losing sight of the target for a couple seconds, so you can recapture that without too much problem. Okay, so here's an example here. The little lines, that's actually the field of view. So when it starts out here, it sees the target over there at 5.2 seconds. It's kind of flying in the wrong direction. It takes a while for it to make that correction. And you can see here it doesn't really care what path it's going. It's head towards the light, and you can see either way it finds there. And if it gets lost, it uses the gyro. So we're regulating you don't really have any control over the height because there's no sensor for height. All we know is we can see the target, so the target is drifting up and down. We can control the wing speed, and we have a rudder on there to control the direction. I'll show you some movies of this. Or should I just this picture here? So this is just explaining. There's a common filter in there, so it builds up an estimate of where the target is and calculates the correcting directions. Starts over there, and it's the target. I don't know what that is. I've never seen that. Somehow I get dropped. Okay, so that's flight just by itself. One of the interesting things at the small scale, it turns out
May I? I'm curious. Do you make any use of optical flow, or
we've got some projects. Optical flow. I think it's a really good mode. We've done some work on optical flow. One of the challenges that we're still working toward is the wings are flapping at about 15 hertz, and the camera is sampling at 25 hertz. So we're completely aliased. We're not above the Nyquist rate. So we've done some preliminary work with using the gyro in combination with the information from the camera to try to recover the optical flow information. Probably what we're going to do is to go to, if we can just get the camera up to 60 hertz, which we can with a faster processor, it gives us more hope for being able to do the optical flow. It is kind of interesting though that most of the optical flow work you see, it's on either fixed wing aircraft or robots with wheels on it, so that the motion is fairly smooth. But here we have this oscillatory platform, which makes things, that adds an extra challenge on there. Thank you. So one of the so we've got the small platforms, 12 grams. One of the things that's interesting is the small scale. You might be able to do this at larger scale as well. Is that we're building mechanisms that are very lightweight, and so we can take a structure that's doing one thing, and we can add some extra mechanism on there and get it to do something else as well. And so that's the next thing I want to talk about, which is a robot where we can combine flying and ground locomotion. It's got some interesting things both from a practical point of view and also just providing a few, maybe addressing it in a very crude way, some issues about when animals started to fly. What would you do with wings that are not good enough to fly? Imagine something evolving. So it's like the offspring suddenly sprout wings that allow it to fly. It's just seems a little hard, right? So what would you do with wings that are kind of like really too marginal to allow you to fly, but maybe they can do some other things for you? For example, gliding, or I'll show a picture. Maybe they help with stabilization, so you can see the use for wings that aren't good enough to fly. So that's a side issue. So I'll start with showing something that does fly and locomote, but we do have a little bit of interest in sort of answering some biological questions about where flight came from. So just as what you're going to see here, this is probably not going to show up very well at all, but this is a ceiling, right? Ceiling, drop ceiling. Why not just fly? Well, you're up in a drop ceiling. You can imagine there's all these wires that hold the ceiling panels up. So it's going to be very difficult to fly in there without hitting those wires. It's actually probably the worst thing for trying to fly without hitting stuff. Very, very hard to see. So in an environment like that, maybe you'd like to crawl. And if you can crawl in that space and still have the ability to fly, that would be useful. Let's show just this. I got clearer videos later, but it does have legs. It works out. So there's the legs, and then you can just go to a flying mode. Let me show you some detail on this. So this is answering the question of what would you do? What good could wings be if they're not good enough for flying? One possibility is stabilization and running. So this is the dash robot with bad tuning. You see it's building up a roll, pretty serious roll moment. But if you put wings on it, it's nice and stable. I just got this comment in a review. It's kind of funny. The reviewer says, "Why are you working on things that fly and crawl? It's like we don't understand either flying or crawling by itself." And I had to convince him. I had to show him this, and go like, "Well, it's actually there's this mode where it's actually maybe easier in this intermediate plane because the wings have a lot of passive stabilization. So now it's actually easier to maybe understand both of those things together than each one in isolation. Complementary." So this is the device built by Kevin Peterson. So starting with the mechanism from the toy, keep the motor. Everything else is carbon fiber airframe, carbon fiber tail, battery at the end for keeping this adjusting the center of gravity so it's good and hover. There is in the Yybird I showed, there's a rotor on the back for steering. This one actually doesn't have the steering control on it yet. And then these carbon fiber legs. I'll show a little bit of how. Basically, there's only one motor here, so it's a very minimal robot, and in that there's just one motor that drives both the legs and the wings. Actually provides an interesting thing if you're thinking about from a power point of view. You've now enforced the constraint that you're not adding extra power for the legs or the wings. There's only a division of the power between those two, and then you can really answer some questions about when is it more effective to fly, when is it more effective to crawl. You can't cheat, there's only one motor. This weighs, it still weighs at the same order about 13 grams. See some just takeoff, and we'll show some more things here. It's just, it just looks very graceful the way it doesn't actually need really a running takeoff because it's got its thrust is enough to hover, so it can almost just take off sort of as a maybe not quite VTOL, but short takeoff and landing. Sort of a head-on view. So you actually have to go slow enough so that it doesn't fly. It wants to fly more than it wants to run. Okay, another use for wings if you're not flying. How about going over really rough terrain, going over obstacles. So here's a vehicle, first I'll show it just with legs, and sometimes they'll get over the obstacle and sometimes not. It doesn't start out very clean. But you see, first time it hit the obstacle and then turned, and the second time it goes over. So it's kind of inconsistent. But if you put wings on there with the legs, now you get it goes over pretty nice because the wing thrust gives you a little upward vector. So again, it's an example where, with the legs would actually have to do quite a bit of work to get up over that obstacle, but the thrust makes that much easier to do. So even if you couldn't fly, the legs might be a useful thing. Okay. There's a really classic work by Ken Dial you may have seen. It's looking at called wing-assisted inclined running. The hypothesis is, going back to the evolutionary question, is that wings could assist animals if they try to escape from predators or to get up trees or to climb surfaces. So at some point if you don't have enough friction, you don't have good claws, you can't go up high slopes. And what Ken Dial was looking at is as birds develop, as they're growing up, they start out, of course, not being able to fly when they initially hatch, but they can still use their wings even from birth. And those wings provide just a little bit of thrust and a tiny little bit of lift, and it actually helps them to climb surfaces. So we were looking at that as well. We got a paper coming out this month in Biomimetics with Robert Dudley, so looking at some of those the evolution question. And just want to show you that it climbs until we get gecko adhesives working, which we'll talk about towards the end of the talk. Provides a very nice way of climbing slopes that you couldn't climb otherwise. And sorry, that one got a little bit truncated, but you can see that without the wings on, of course, that's just going to slide right down. And so the wing thrust lets you climb surfaces that you couldn't climb otherwise. So maybe another example where wings plus legs is easier than just legs alone. So we mentioned we've got the board we're using. It's got an accelerometer on there. So it's looking at some of the interesting issues of what's going on the ground. And so you've got the forces on the robot are the thrust and lift forces from the wing, as well as the ground contact forces. So we're looking at the question of what is the effect of phasing between the legs providing thrust when they contact the ground and the wings providing thrust. So for example, if you have a negative component of lift from the wings, that could drive the legs into the ground. So now when the legs move forward, you've got greater effective friction force. You could get greater thrust from the legs forcing them into the ground. Or you could get this greater thrust because you're in this almost flying case here. So we looked at a variety of cases. We've got one, we just stuck some wheels on there. So we said, okay, there are now no leg acceleration forces into the ground because there's wheels on the ground. And you can look with wings only. This is the acceleration. Look here, it's going up to 5 Gs. This is in the normal direction. So with wings alone, it's going very smoothly. If you have wings passive, that means that you have the wings on the robot, but there's no, they're not doing anything. They're just fixed wings. You can see the classic big dips here between the phasing between the normal and the lateral acceleration. And if you have, if you add in the force from the wings only and the wings passive, you add those two things together, this is combined. So if the forces work by superposition, that is, you could take just the wing forces and just the leg forces, and you could just add them together. Mathematically, that's this curve. But in fact, when you actually run it, you can see it's actually very smooth. So it's providing some self-synchronization or self-coordination. Provides a very smooth operation here. This is just the difference between the two. So we're just starting to look at trying to answer the question of what should the phase be between the wings and the legs. Right now we have to change the phase manually by just moving the crank arm and trying it out at different positions. But we think if we put a transmission system on there, actually be really interesting for different types of material, media, whether you're running along on a horizontal, soft, squishy surface or climbing slopes, being able to change the wing and leg phasing, we think would be very interesting for different locomotion modes. Efficiency was something. It's a very interesting question. I don't think we're there yet. What we can say. This is the cost of transport, joules per kilogram per meter. This is about an order of magnitude worse than you get with a nice robot. So it's pretty bad so far. Not too surprisingly is if you're going really slow and you're trying to run the wings, these wings are just generating drag. They're not doing anything useful for you because your power consumption is terrible. So if you're going slow, we'd like to have a clutch on there so you can turn off the wings or fold the wings so they're not providing drag. If you're going at high speed, this is going like 9 hertz, not enough to fly. This is getting close. Liftoff is at about 13 or 14 hertz for the wing speed. So going fast. Now, just trying to go with the legs and the wings passive. Now the wings aren't doing much at all for you, and you're better off with just flying without the legs at all. But the relationship here is that with the hybrid, you're kind of in between these two extremes. So from a locomotion efficiency point of view, this may help. We think we can do better by improving the leg tuning and coming up with better transmissions to exchange the power between the legs and the wings in more optimal fashion. So how do we build robots? Then we're going to switch to the compliant and ambulating Millirobots. The process we've come up with is a successor to the process we built for the micromechanical flying insect back in '98. It's actually a successor to something we had with probably Chris Feaster surface micromachining project with silicon back in '91. So we've always been thinking that we want to build structures very, very easily. We want them to be very lightweight. The way to get lightweight structures is to take flat sheets and build shell structures, because shells have really good strength and weight properties. So you want to build things flat, and you have to and flat is easy to fabricate, and so you want to build things flat and then fold them up. And so the process we've been using recently, this is switched from originally silicon then to carbon fiber. We still do some carbon fiber, but now we're using a poster board, very, very low cost materials. That's nice too. It's isotropic, very cheap, non-toxic, etc. Take fiber board, laser cut the gap in between. You fill the gap with a flexure layer. This flexure layer could be something like polyamide or polyester. Run through a lamination process. Finally do the final cut, and now we end up with a series of links which are approximately rigid and flexures where you bend. So you can add as many flexures, as many joints as you want to your robot structure, simply by controlling a laser cut. So we think a lot of our robots will have 60 or 100 joints in them, and it really doesn't. 60 or 100 movable joints, and then we have rigid parts of the structure. We may add another 60 or 100 joints in the structure that are designed to bend into a shape and then stay fixed in that location. So hundreds of joints doesn't bother us at all. But it would be I don't even want to think about making that with ball bearings and drill press. Just give me nightmares just thinking about it. I know I'm not any good at that. It takes too long. So this is the outline of the process, maybe a bit more pictorially. Starting with 1, there's the CAD design. 2 is a cardboard cutout. In this case, there's a top half and a bottom half. In step 3, a adhesive and a flexure layer is placed between. Step 4, it's run through a laminator. 5 comes out of the laminator. 6, final cut. You can see the pieces. These are legs. That's the body pieces. There's a folding step glued together, and there's the robot. Recently, we come up with a way we like to change the configuration of the robot without having to rebuild it. This process takes somewhere between 1 and 4 hours to do the manual assembly. Usually, I'd say steps 1 through 6 are probably 20 minutes or something like that, but steps 7 through 9 might be 4 hours or something like that. So build up a robot and not make any change. What we've come up with, I'll talk about in a minute, is this idea that we can print connectors onto the links so we can change the robot very easily. Let me show you just an example of an older robot from a few years back. This is this kind of a cute thing. Oh, I should mention, yes, this reminds me to say that this is a scalable process. So we can build robot structures from palm size, weighing, say, 35 grams, down to milli size. This is about 2.5 grams. And of course, the same process has been used for building small flapping devices, which Rob Wood almost has flying now. Now he's got down into probably about 20 milligrams. So the size range from 3 orders of magnitude in weight. Characteristic dimension, probably the smallest ones would be, let's say, 5 millimeters to 150 millimeters. So a factor of 30 in linear dimensions, all using the same basic process. And we're tempted to see if we can scale this up with just a bigger laser cutter and make these things out of plywood and see if we can get something to grind around on. I don't know if that's going to work well. So this is, yeah, showing there's 5 times scale. It's actually, of course, there's some design differences because the joints are, the scaling of the joints gets a little bit tricky, but it's basically the same design. In fact, what we did here is this cardboard one was originally, we built this because we said, oh, the small one's going to be a real pain to build. It's going to take, days to get all that working together. Let's build a big one first, and just to see how all the kinematics works. And then, it's actually, here's a Slava, who's an undergraduate in the lab at the time, is now just finished a PhD at CMU. He said, well, we put a motor on there and see what it does. It's just cardboard, it's going to fall apart. When we put a motor on it, it's surprisingly robust, and it's turned out to be a good way to build the robots as soon as people get over the fact that it's made out of made out of poster board. Of course, it's green and recyclable and non-toxic. all that good stuff. Okay, so this is the small robot we built. This is at the time, I think, was one of the smallest autonomous robots. Was actually walking on the stairs. Took a step or two. This took a real step. Of course, much larger than what Sarah made, but it was at the time it was autonomous. So connectors. These are. So we have this cardboard process. We want to come up with a way to make links that we can attach and detach very easily. These things are bending like this. If you just kind of put nuts and bolts in there, those bolts are going to interfere with everything. Of course, it's going to make it very, very expensive, hard to put together. So we came up with a way that's compatible with the process. We had another, basically, lamination or molding steps. The connectors are molded onto the poster board material, so we can change the configuration. And the way we came up with doing that is basically use a laser micromachining to make a mold out of silicone rubber, and now we can put these connectors onto the cardboard surface, and they're very low profile, of course, very low cost and compatible with the fabrication process. And this is what they look like. It's an AA connector, so you don't need two different parts. Whatever, you put the same connector on both pieces, and it'll go together with itself. Just small ridges, about 125 microns high. And it works. Here's sort of after being tested to failure. So if you overloaded, things kind of get out of shape, but it actually still works pretty well up to 10 cycles. This is not 10 uses in the proper way. This is 10 times after it's been torn apart in a way that's not designed to preserve the connector, and we still maintained maybe about half of the original strength. And these numbers to get a ballpark on here, yeah, newtons per square centimeter. Right? That's the robot is weighing 300 kilonewtons. We're getting strengths of 30 newtons per square centimeter. So these connectors are plenty strong to hold the robots together. And this will allow us to do things like change the legs, change the number of legs, change the body segments. We can do modular robots as well, sticking pieces together. So some ambulating robots. This is from a couple of years ago. This is the dash robot called Bergbreiter created. And it's got some nice features. We were very pleasantly surprised at how well this cardboard robot works. This is the first cardboard robot we had, which was really taking advantage of the dynamics of this lightweight structure, taking advantage of the dynamics and the compliant properties. And this goes back to my early slide there. It's got, of course, no representation of the obstacle. And you can say, oh, it's just getting over there by luck. But there's a little bit more going as well. You've got dynamics. You've got, you're building up large amplitudes of motion. You've got a lightweight robot. And just think about the statistics of that. It's going to be able to overcome that obstacle. And this is just showing the resilience. It's a very, very lightweight structure. There's nothing, it twists very easily, and at least poster board is very much more resilient material than carbon fiber that survives. It's sort of that in that picture there. It's actually thrown against the ground. We've also dropped it off in 8-story buildings, and it reaches terminal velocity, and it doesn't hurt it. Pretty robust, surprisingly robust. This is one of those occasions where just build something and we're expecting it to kind of work, and it just worked much better. Once a decade or something where it like just works so much better than you had hoped it for its work. And it's sort of robust like insect, sort of the exoskeleton, and it doesn't have brittle bones. It's all very resilient. And it turns out, we look at this classical lots and lots of animals. It turns out that you can look at them as if they're a spring-loaded and inverted pendulum with a classic storing energy in the leg and releasing it and reaching this gate like this. And look at this for 6-legged, 2-legged, and 4-legged, 8-legged. Right, there's a lot of this work done by Bob Full, coming up with this equivalent pattern. And it turns out, if we look at our robot, it does a very similar thing. So looking at it on a force plate, you see here's the weight of the robot, and the normal force is oscillating like this, and fore-aft force, you see foot plants, it decelerates, here it accelerates, moves along, and you can see it does have here an airborne phase, so it's looking like a dynamic running animal, and also looking at the equivalent stiffness. This is Dash. It's also in with all these animals, that over many orders of magnitude have the same relative stiffness. So it's looking very much like a dynamic running robot, very, very similar fashion. One of the things that's really critical on these is the leg tuning, and coming up with a good leg tuning is still very much an open question in the dynamic robot research community. Saw this in the movie. Yes, Crushers. This shows a little close up here. That doesn't look very here and here. It doesn't look very rectangular. It's really distorted quite a bit and very, very dramatic.
Question?
Yes.
Is this flexural layer process that is involved in making legs, the legs we see here, as well as other parts, is that understood well enough that you can sort of, if somebody said, I want a leg with this equivalent slip model stiffness, then you can sort of program the process to put together a leg like that?
Let me break that question in 2 ways. One is, if you said, I need a leg that has this particular stiffness property, that we could do. I think it would go from the manufacturing. The other part of the question is, what should the stiffness property be for this robot so that it runs well on carpet, or so that it runs well on concrete, or so that it runs well on rocks? And that's an open question. I've been very impressed. There's papers recently where people trying to answer this question that they don't have a good analytic solution for it, so they're building robots where there's actuators on the legs to change the stiffness, so they can try to find what the stiffness should be by building the mechanical model and tuning the stiffness, which seems like it's, so that's giving me an indication that it's a fairly tough problem. People haven't figured out how to answer that, and they actually go to the work of building systems. Answer the question. In fact, it's sort of Dan Kotichek's lab, who would certainly not be averse to finding a nice mathematical model to answer that question. So if he had an answer mathematically, I think we would have seen it by now. He's building robots with tunable leg stiffness. So it's an interesting thing. And you saw that the one, I showed you the video with the robot without the legs that was doing that roll. It could have been a very simple change in the stiffness parameter of maybe 20% on the legs, going from running like you see here to the previous case where it just does a roll. Because these systems are very, very, you want them to have low damping because they're running dynamically. It's as you let the energy build up in the system that you want for forward propulsion, you don't want it to be generating roll and pitch moments. So it's a very tricky thing. And I don't have a good answer for it. We're working also with Peter Avil, just seeing if we do a learning approach on this to it's a huge space and try a learning approach to find a good link. So lots of robots. Some variations. We're finding the process is really convenient. There's all sorts of variations. We want to understand all-terrain mobility. By that I mean I want a robot that can climb on the floor, climb on the walls, climb on the ceiling. This is Paul Berkmeyer's robot. Same construction technique, single motor, somewhat similar kinematics to the other robots. And looking at, again, coming back to the passive mechanics, how do I climb now a loose cloth surface? So people climb walls with claws, but with a loose cloth surface now, the surface is moving away from you, and so your timing and your forces actually become quite critical, right? If you just slap against the wall, the whole robot will start moving on cloth. So this robot's built, again, with a passive mechanism. Fairly straightforward design. There's a 4-bar mechanism there. Here it's unengaged. Here it's being pushed into the surface, and here it's being pulled away. So you want to have an anisotropic contact with the surface. So when you engage with the surface, it should provide you a force so you can thrust in the upward direction. But when you pull the foot out, you don't want to have to yank the foot out, or you're not going to be able to run dynamically. So again, there's a passive mechanism which is critical here for the engagement with the surface. The robot is running fast enough. Imagine a robot's running at 15 hertz. You could, maybe at this speed, you could put a motor in here and try and actuate that as well to control things. But it's really, I think it's both not necessary and the extra complexity from an actuated foot's really going to slow down your whole robot, so it's not going to work as well. Just a detail issue, I mentioned the control here. Okay, so we built the same mechanism now with no joints in it, so it's just a rigid connection. I can show you, we did some testing on with a force sensor and a motion stage, so engaging the cloth and seeing what the pull-off forces are. So you can see, this is looking at, so it's a little bit blurry, at various angles here coming in to the surface. So here is an example where if you had just a fixed joint which didn't have this, a fixed linkage which didn't have the ability to rotate, you'd have this huge pull-off force. You don't really want that. You want to be able to the foot to engage, provide a strong force in the downward direction and negligible force in the release direction. Starts out a little funny because the compression, you can see it's running up the surface, loose cloth. Very lightweight robot, weighs on the order of 15 grams. Sort of at the end here, you can watch there, just throw it against the surface, and it latches on. And begins climbing. We're also looking at, again, appendage is a pretty interesting thing, and we talked about tuning the leg stiffness for stability. Sometimes you want to destabilize. So we've got a simple model for how you could destabilize a system to cause now a yaw moment if you want to steer. And we look at changing the stiffness by changing the feet here and get the robot to consistently turn left, right, or go straight. I should say consistently with some error about there. At least you get it nominally by changing putting a stiff leg on the right midsection, get it turned left, or stiff on the left midsection, get it to turn right. I'll show that in the video. This is at 1/10 speed. So the robot's coming up, and can you see that at all? Sorry about that. Yeah, and so it's going to be taking a sharp turn there due to the light stiffness. We're also looking at just another design. The newest robot, Octoroach, want to look a little bit at a more controlled form of steering. So looking at, so we kind of compromised on our principles and added extra motors. We have like put 100% more motors on the robots. So I've got two motors, one for each side. And we took the previous robot, which was driven by one motor, and both sides have phase locked mechanically. And now we're exploring having each side driven independently, which we think gives some pretty interesting possibilities of controlling steering, of course, and also we think we can now do some control. For example, with roll moment, if we want to do bank the robot or do things like that. And just to give you an idea, just to start, to see what it does with two motors. So we can do a turn in place, which is hard to do with a dynamic steering approach. So again, this is at slow motion and using a transmission block that was Paul Samuel, who's Maryland company that had designed for us. So this is a heavy robot, it's 35 grams. So you can see it's got some interesting dynamic. Okay, so the last part of the talk. So I mentioned all-terrain adhesion, and we think this is going to be really important because I showed you the video from Bob Folder's. At some point, there's no amount of thinking that's going to allow you to go up the wall. It's either you have the adhesion, or you have the friction force, or you don't. You can think about it all day. You can best processor in the world. If I don't have adhesion, I can't accomplish my goal of all-terrain mobility. And then for applications like, how would you possibly go into a collapsed building with all this rubble and concrete and surfaces that are just all sorts of crazy angles if you don't have the ability to go over any surface. So what we're looking at is actually, in a very significant way, it's a extension of the work I guess I did for my master's thesis of looking at grasping of objects. And you can see here grabbing something with two fingers. I'll show a movie of that in a minute. And instead of grabbing an object with two fingers, you say, okay, what's actually the hardest thing to grab with a hand? The hardest thing to grab with a hand is a flat surface. So to grab a flat surface, we need to have some adhesion forces. So where do the adhesion forces come from? At the nanoscale, the adhesion forces come from van der Waals forces. So there's always attraction between, unless you're at absolute zero, there's attraction from instantaneous polarizations between the molecules and the two materials, and so you get forces between surfaces which drop off really quickly, 1/r⁶, 1/r⁸. They're only effective over distances of a nanometer or so. So to take advantage of those forces, you need to be in very intimate contact. Conventionally, you just use a piece of Scotch tape that gives you really great intimate contact between two surfaces. However, if you try to put Scotch tape on your robots work great for about 10 steps and it gets fouled up with dirt. So you need something that provides intimate contact with the surface, but you have to have this aspect of controllability. That is, you can control the adhesion. You can adhere to surfaces, but you should be able to de-adhere to dirt that you don't want to foul up your feet. And so this is what I'll talk a little bit about this. I think it's going to show one ancient, sorry, undergraduates. 2000s, like, what was it? Like kindergarten or something then, right? How can that be interesting? That's so long ago. Okay. So this is, again, showing some passive behavior. There's two fingers there. There's compliant springs in the fingers. And what it's done is basically it's automatically finding an equilibrium so that if there's any perturbation of the position of the object, it'll slip and go back to its stable equilibrium. And because you have this stable equilibrium in the grasping, now you can do all sorts of complicated manipulations. And I should say this is all done, it's an open loop feed-forward fashion. There's no sensing. There's just a programmed approximate position of where these parts are. I'll should mention these are pretty small parts, and they're a couple hundred microns in size, and they're held in place by the passive mechanical properties. Clock's not as fast as it. Okay. So eventually the errors accumulate. This is actually where we started from in thinking about, well, we have these passive properties, and we're going to be engaging a surface, and I'm going to use van der Waals forces. So I'm going to need each of the van der Waals force of each finger is going to be really small. So I'm going to need hundreds of millions of fingers. And let's see, so let's see, so we'll put an actuator on each finger and a sensor. Okay, let's see, just do the numbers I would say. So I've got, let's say, a billion fingers per square centimeter, and just the wiring, wire a billion actuators, and hook a supercomputer up to that to drive, because each finger is needing to be moving at probably like a 10 kilohertz resonant frequency. Nowadays, say 10 billion elements at 2 degrees of freedom each, 10 kilohertz, and the computation complexity becomes pretty big. So the forces us to come back to this idea of a passive behavior, passive compliance, and so the mechanism has to be designed to be stable and work on its own without a lot of external control. And this is the gecko has had this figured out for 100 million years. Lots of really unique properties here. Full hierarchical structure. Attaches in one direction, detaches very easily. Very easy to engage, easy to high pull-off preload ratio. Pull it off easily if you want to, sticks to anything, cleans itself, doesn't stick to itself, and doesn't adhere unless you want it to adhere, and doesn't leave any residue. And so we've done a lot of things in the last 10 years towards building artificial materials which do this, just for the fun of it. You might think of applications, automobile tires, high coefficients of friction, gloves. But let me talk about the principles. Why does this work? Rough surface compatibility. You want something very low stiffness so that you can basically can flow onto the surface, but in a controllable fashion with these fibers. And it's controllable, and let me show you an example of why it is controllable. Fibers come in very small contact area when they're straight, but when you apply shear force, they bend over, contact area increases dramatically, then gives you adhesion force to remove, you reduce the force. I'll show you that in a video from 3 years ago. So you can maybe see at the top there, that light area, that's where the contact area is increasing as you're pulling. Builds up pretty good forces. And it's actually designed to have very low peel strength. So if you want to remove it, we'll see that in a minute. It just peels right off. So if you imagine the robot foot comes in, engages, can apply a large force, but then when you take the next step, it's going to peel off very easily. That's shown in the next bit. These gloves are always a good touch, makes it more scientific. But it turns out the oil from fingers is got very low surface energy. Actually, destroy the adhesive effect. This adhesive effect is working on, in a limited case of glass, making it work on rougher surfaces is much more challenging.
Question? The experimenter was pretty careful not to let the weight come down too rapidly, like jerk down.
Yes.
So presumably that kind of impact loading is a problem. Exactly what happens during such loading in the
So what would happen in this case is this material, it doesn't have any of the hierarchical structure, so it's got very low peel strength. So if you drop the weight, it would start an oscillation, and then if the oscillation came, it would provide a little peel.
Sideways.
This was sideways would cause peel. So the later structures it can handle it. To actually make it an effective climbing adhesive, it does have to have a little bit of peel strength, maybe about 10 degrees or so. The way we make this is basically molding into nanopores and then etching. This is one of our better experiments to show shear stress. We got up here to 30 newtons per square centimeter. That's pretty strong. Imagine again the robot's weighing maybe 30 grams, 300 milliliters. So it's a very small patch of this. We're here. This is on glass again. The interesting part here is that you're seeing this, what's called the frictional adhesion effect. As you engage the fibers, this is the shear, here's your preload down here, very small preload compared to the shear you're getting. Notice as you're dragging, this normal force is getting negative, so the fibers are pulling into the surface, and this will then allow you to hang on, to actually hang on even an inverted surface. Picture the fibers. And this is the critical, that's the business part of the adhesive, that it's doing something more than just a simple friction. The good news and bad news is that, hey, this is working so great, and it actually works here. It's still working with 10,000 cycles. It's adhering so well that even with polypropylene, which is a material of about 2 gigapascal modulus, our adhesion force is so strong that we're deforming the plastic. You can imagine the stresses that's required. It's probably up in the megapascal range to deform. Polypropylene is a pretty hard material, right? If you're doing like milk jugs, polyethylene, it's probably about 5 times stiffer than that. So it's a really, really tough material. And even with the tough material, the adhesive force is so strong, it's deforming. The other interesting thing that's going on is even though it's completely deformed, we've only lost about 30% of the force. It's very not sure exactly why this shape is still working, but it is. It's sort of like self-adapting to the surface or self-polishing. I think that's an interesting effect. Very directional. Let's just finish up with 1 minute on the particle adhesion. I think it's a really interesting issue. How do you get something which can, here's a particle, the particles maybe they're larger than your the business end of your gecko adhesive. How do you get something that, it's got a choice, a particle could adhere to the surface or to your fibers. So you need to build something that's actually at an equilibrium, where you, if this is too adhesive here, or you don't have control over it, your material will just load up completely with particles, and you won't be able to climb things. So you need something that can shed these particles and give the particles a choice between adhering to the wall or adhering to your material. In gecko, you can see it cleans, starts out dirty, and after it takes 8 steps, you recovered about 30% of original force. The materials we make are they're not very adhesive. Say this is air cleaning, just blow it off with air, particles come off. Silicone rubber, it stays stuck. We've built, we can clean after about 30 steps. This is with gold particles. We start out here dirty, particles come off, and we end up with, we recover about 30% of our original force. And pictures look kind of dramatic. At the top is polypropylene fibers, you're spalled. After the steps, most of the particles have come off, and it's adhesive material. And as you'd expect, like a Scotch tape here, you put particles on, and you just end up with a sea of particles. And those are not coming off. And various hierarchical structures. Let me just go to the conclusion then. So these are the principles I'm coming up with for biomimetic millirobots. Very much think we need to go with the flow, not try to control the system in a way that forces it to do things that it doesn't want to do naturally. It's not going to work from an energetic point of view, not going to work from a complexity point of view, not going to work from a bandwidth point of view, not going to work without perfect sensing. So go with the flow, whether it's compliant grasping of local equilibrium for gecko adhesive or passive matching to the surface topology for the legged robots. Taking advantage of passive stabilization. You want your system to be robust to disturbances. If you're running at the legs at 15 hertz, leg contacts occurring at 30 hertz, there's really not time with the bandwidth of most typical systems to do anything about it other than to rely on passive stabilization to keep you from losing steps or flipping over. Dynamics are really important. We really like systems high power and weight ratio. This allows our robots to plow through things without having to think about it. So it's an important principle that we can take advantage of because we're building our robots with thin shell structures, high strength to weight ratio, and we can put actuators on there, keep power density up. Typical rule of thumb we like is about 100 watts per kilogram, which matches the natural animals. Low internal dissipation, high frequency average out disturbances, and final thing is we think it's good to design your system, work around the equilibrium, and then add perturbations as you want to get the system to go where you want. So with that, thank you very much for your attention, certainly, and thank all of my collaborators over the last 10 years who've made all this work possible. So thank you very much.
Any questions for Ron?
So how's your process different from the, when you're talking about the gate process, different from the macroscale?
Yeah, so Mark Kukowski's got he's using a softer polymer. So he's using PDMS and soft polyurethanes. What happens is if you want to, if you start with a material which is adhesive, it's actually much easier. So you start, silicone rubber, just as you make it, it's already sticky. So you take that and put it on glass. So what he's doing is starting from a sticky material, adding hierarchical structure on it. He's made it controllable by putting wedge shapes in. So as you start out with a tip contact, but as you shear it, contact area increases. So he's got controllability. So it's actually a very decent material. Where we think it may have some limitations is this whole self-cleaning aspect, because you start out with something that already likes to stick to things a little bit too much. So we start with polypropylene, which is actually, or you can imagine like high-density polyethylene, right? They use it in artificial joints because it has very low friction. So we start with something that doesn't like to stick to things and make it adhesive. So he's got robots that already are climbing very, very nicely. So he's got better climbing robots than we have, but he's got materials which probably are a little bit limited for the final applications we're thinking about because of the self-cleaning machine.
So a question similar to Christian's question. So if I wanted to write down some models of the robots for designing them, for figuring out what they can do, can you give me a sense of like, if I did so naive things, just had a sort of maybe friction model and rigid bars, would I do pretty good, would I do really badly? Like how hard is it to try sort of write down equations for what these things do?
So we're starting now, I think we know enough now that we have some collaborators who can start to do some modeling on these things. So we're hoping that will be helpful in some regard. Now, from a design point of view, maybe I can answer your question in terms of how many iterations does it take to go from a concept to like the Dash robot, which is running along so well. Let's say about 2 dozen.
Okay.
This is probably a good where there's so many details that get worked out, everything from the joint collisions inside the mechanism to things peeling because the fixed mechanical structure was missing reinforcement plates. There are peeling moments in there.
Okay.
So a lot of that we think could be codified in the model. So or just actually probably more likely just design libraries. So when you put it, when you're building a joint like this, you make sure you have an orthogonal faceplate to keep it from peeling.
Yeah.
But it's a little bit of a drawback to the process because it is, in an hour I can have a new design, so I can change it out, and which is great for creativity. So there's got to be some balance because if you go afterwards and go, oh, didn't you realize that just wasn't going to be a strong structure? But I don't want to cramp the creativity. So someone's got a good idea, they may come up with something that we didn't realize was possible. So it's in the end, like you look in terms of a graduate student career, right? So if they're spending maybe six months getting something working, that's probably about the same timeline for any robot construction project.
All right.
So what were the robot configuration where you're using 2 motors? What kind of motors were you using?
It's the same motors. They're just all these motors are just coming out of toy aircraft.
So you were then synchronizing somehow?
Well, actually, so we started out with, we're just starting to look at the synchronization. We actually started out without any active synchronization. In some cases, running on carpet, it self-stabilizes, which is kind of interesting because there's some simple things there. The feet be hitting on one side, and at the point where the feet on the other side are hitting, so it's kind of they're fighting against each other. We're putting some feedback on there to look explicitly at what happens with, because now you can do all sorts of things. We can do the pacing gait. And actually, turning is kind of an interesting thing as well. So we started out with a turning where just one side goes faster than the other. But if you keep the two sides synchronized, now you can during part of the leg stroke, speed up one robot versus speed up part of the leg stroke versus the other part, so that you can